All right, so let us begin now. So welcome everybody to Elad Farhi's PhD seminar. So brief introduction. So Elad completed his BSc in aerospace engineering, cum laude, here at the Technion in 2013. He worked about 4 years as an R&D engineer in the IAI, where he was, as he claims at least, the youngest in the engineering development department to ever receive the Excellence Award of the director. And then he got bored there, I guess, and he returned to the Technion to complete his master's degrees. And on the way, he moved on to direct track PhD. He's now in. All this in the as part of the Technion Autonomous Systems program under my supervision. And we are both really excited to share with you Elad's research, which is very cool, I think. So Elad, please go ahead.
Thanks, Vadim. Well, hello. Today I'll review my work towards a PhD under the supervision of Professor Indelman on joint incremental inference and belief system planning for online operations of autonomous systems. So to make our research more accessible, I'll bear the math down to the absolute essentials. And if math excites you, don't despair. We share your love, and that's why our papers and my thesis are full of it. So let's start with understanding the motivation of our work. Inference and decision-making under uncertainty impose a fundamental problem in both autonomous systems and artificial intelligence. At their core, autonomous systems require two basic blocks: inference and perception, which obtain information from the environment and estimate state variables using existing data, and planning, tasked with choosing the next optimal action given objective and current belief. The realistic problem is computationally interactable, hence usually approximated, since any reduction in computation time helps paving the way to real-time performance. While there are many variations of AS and AI related problems, in this work we'll consider the original unapproximated interactable formulation with active SLAM as an example. Now let's better understand the inference and belief system planning flow as done today. First, we have belief system planning tasked with providing us with the next optimal action. We then execute this action, get new measurements, and use them to estimate the state. And for the next time step, we are using last posterior to create a new plan for the next time step. Execute this action, get measurements, and update the last inference to obtain the new one. And this goes on. While this is the state of the art, we propose a conceptual change that, to the best of our knowledge, has been overlooked. Before presenting the conceptual change, let us first understand the problem with the existing paradigm through two simple examples. Starting with the inference update. Let's say that tomorrow you have a job interview for your dream job. You'll probably spend the rest of the day going over all questions you might be asked about. And by the time you're done, that's how your brain will probably look like. Now, the interview day has arrived. What would happen if you'll be asked on a subject you didn't cover, close to what you've covered, or identical to what you've covered? Which would result in the quickest answer by your part? Now, let's define the case where the subject is identical to what you planned for as consistent DA and the conjugate as inconsistent. The current formulation in autonomous systems will always rethink the answer instead of building on its plan. Now let's review belief space planning. Imagine a wazeless world in which you need to travel from home to work for the first time ever. You consider all possible routes before exiting and choose the best one in terms of distance and time to target. Now, once you selected your preferred route, you start driving. After a while, you notice a possible blockage in your route. What will you do? Will you plan everything from scratch or just update your existing plan with the new information? Well, this is a relatively simple problem. We consider a partially observable Markov decision process, or POMDP setting, which in comparison looks something like this. We only know what we saw, and also this is with some level of uncertainty. Current top of the line in autonomous systems do not incrementally update the previous plan, but just create a new one, which bring us to our vision. reusing calculations and information across inference and planning for improved online autonomy, in particular in unknown environments and high-dimensional state spaces. Our main contributions are introducing joint inference and belief system planning, or JIP, a paradigm shift from the common separation between inference and planning, a patented approach for reusing belief system planning for efficient inference update named Ruby, and a patented approach for incremental expectation belief system planning named iX-BSP. If that's inference and belief system planning today, Ruby suggests inference update using previous planning sessions. And iX-BSP suggests updating previous plan with the new information. Now let's briefly cover some notations and formulations, so my talk won't be in Chinese, but in English. So subscript t given k refer to time t while current time is k. Capital X t is the joint state vector up to time t containing all robot poses and landmarks, i.e. the smoothing problem. Z1 to t given k are all measurements up to time t while current time is k. Same goes for actions denoted by u. B of x k given k is the belief over the state at current time k. Similarly, B of x given k plus I given k is the belief at future time k plus I. H represents the history of actions and measurements, and without the last measurement, we denote it as H minus. Now this is the research outline we'll cover, starting with JIP and the related work of it. So on the similarities between inference and belief system planning, Toussaint and Todorov worked on approximate solution to the Markov decision process case for inference and planning using inference optimization method. Todorov investigated the duality between inference and optimal control. Kobylarov and Ta worked on unified computational frameworks, but till this day, to the best of our knowledge, there is no joint paradigm for inference and decision-making under uncertainty. Interestingly enough, inference and decision-making in the human brain are tightly entwined, providing motivation for AS equivalent. Now, our proposed JIP model encapsulates both inference, represented by the horizontal errors, and planning, represented by the diagonal ones. The full model is 3D rather than 2D, with more diagonal errors branching in and out of the screen to represent all future possibilities. JIP also enables new connectivity, starting with Ruby, which is the shift from the conventional Bayesian inference updating inference using planning rather than the last inference, visualized by the connectivity between inference and the corresponding prediction from planning, marked in red. The second connection we introduce is iX-BSP, allowing us to incrementally create the new planning session by updating previous ones. Now let's dive into each of which, starting with Ruby. The main contribution our work on Ruby offers are, contrary to Bayesian inference, efficiently update inference using precursory planning for exact methods for updating inference, using belief system planning under the assumption of consistent data association and Gaussian models, a paradigm for incrementally updating inconsistent data association, and comparing Ruby to the current top of the line over both simulative and real-world data. Let's start by understanding what is considered today as top of the line in inference update. Let's say we're at current time k with an updated estimation for the joint state vector. During planning, we propagate current belief using future measurements, while the purpose is to provide with the next optimal action in reference to some objective function. The objective for horizon of L steps ahead is defined by the cost over future belief and action for each of the L horizon steps, while accounting for all possible future measurements. Once we have the optimal action, we execute it, get measurements, and use them and the last known state to perform inference, which provide estimation for the joint state, where the belief is comprised out of a prior, all motion models, observation models, and the data association, which provides the triplet association between pose, landmark, and measurement. Under a Gaussian distribution, we have a simple solution via maximum posteriori estimation. Using nonlinear least squares and factorization, we can get to an upper triangular matrix R, which can be solved via back substitution, where the Jacobian matrix A and its square root R are affected by the dA and belief derivatives, and the right-hand side vectors B and D are affected by the measurement values. This is the state of the art in inference update, and we propose a conceptual change that has been overlooked to the best of our knowledge, updating the precursory planning in order to get the posterior inference. If we compare inference and precursory planning, we can see that they differ in dA and measurements, which bring us to a temporary simplifying assumption that we will later relieve of consistent data association. Assuming the dA is consistent, the R matrices of planning and inference would be identical. Hence, in order to solve the inference problem, all we need to do is update the right-hand side vector with the measurement values. We devised 4 methods to do exactly that. The OTM method is true to its name and use orthogonal transformation metrics to update the measurement values. And the DU method, also true to its name, uses downdating and updating in the information space to update measurement values. Each of them has a derived method, which considers updating only the observation values rather than also unnecessarily updating the motion-related values. We denote it by the O addition. Moving to some results. We performed continuous belief system planning, the POMDP case, in unknown static environment. Our 4 methods implemented in MATLAB were compared to standard batch approach, denoted as STD, and current top-of-the-line ISIM2 efficient methodologies through a CPP wrapper, denoted as ISIM. The robot was required to visit 5 goals while not crossing a covariance threshold. We considered known models with additive Gaussian noise, and of course, consistent data association. On the left, you can see the synthetic world, represented by the numbered goals and green mark landmarks, as well as the robot's ground truth in blue, and estimation in red. The ellipses denoted uncertainty, and the yellow go-around marks a large loop closure, meaning seeing once more the landmarks first seen around the first go. On the right, you can see the considerable reduction in inference update computation time along the entire mission. On the left here, we can see the per step computation time performance. In green, ISIM, current top of the line, which bested the standard approach by an order of magnitude. And zooming in on the right, we can see that our methods outperformed ISIM even per step. Focusing on the best 2 methods, we can see that OTM00 is more robust to loop closures as well as having the lowest timing. And so we will continue our work using OTM00. To facilitate Ruby, it's time to relax the simplifying assumption of consistent DA and account for the possible inconsistency between inference and planning. Once it's dealt with, we can revert back to updating the measurements using OTM00. Using QR update, we can incrementally update the data association inconsistencies. On the left, for present time k, a prediction for time k plus 1, in which we think we'll see the landmark LJ. On the right, the present time k plus 1, where we in fact did not see LJ, but saw Li as well as a new landmark LR. This is a simple example for inconsistent data association. In order to update the data association, we use belief graphical representations, factograph, which after linearization and factorization get to the Jacobian form, or after elimination get us to a base tree, which is equivalent to the QR decomposition of the Jacobian. We start by locating the directly involved states in the factograph form, the red and green, locate them in the base tree to isolate all involved states in blue, which allows us to detach the relevant part of the factograph, the mid-upper picture, and update only it. We then re-eliminate this small factograph and reattach it to get the updated base tree and factograph. Now let's put Ruby to the test, starting with some simulation. We perform the same simulation, but this time without forcing inconsistent data association and using 12 goals and more landmarks. We use UDOTM00 to denote the method which updates data association and then uses OTM00 to update the right-hand side values. On the left, the simulated world, marking also 2 loop closures for reference. On the right, the cumulative data of inference update throughout the mission, with a breakdown of the contribution of DA update and right-hand side update. As an after fact, in this simulation, 50% of all measurements were with inconsistent data association. We can see the orange spikes in timing of our method on the left correlates to the required DA eliminations on the upper right in dotted orange, which means that better DA prediction should further improve the timing results. Moving to real-world data. We use the well-known Kitty dataset to compare UDOTM00 to ISIM. Kitty is a passive SLAM dataset, so before each inference session, we perform the planning session over the optimal action sequence. We used only the monocular stream. The robot started from an uninformative prior over its initial pose and with no prior knowledge over the environment whatsoever. Here, we also compared the estimation error using the supplied ground truth. On the left, we can see the estimated world and track of the robot, where each point in the track corresponds to a monocular picture from the Kitty dataset. On the left, we can see the computation time performance with a breakdown of DA update and right-hand side update contributions. Moving to a per-step analysis, on the right, we can see an interesting breakdown of the involved factors. In blue, all factors added in current time under regular Bayesian inference update. In red, the segment of them involving variables that are already part of the state. So the gap between them is actually the number of new states added per step. In yellow, the part of them we managed correctly to predict their DA, and so to reuse from previous planning sessions. Without using a special mechanism for predicting new states, the red line represents the best we can hope for, and the yellow represents the performance of the simple prediction mechanism we used in this work. We present here the absolute difference between Ruby and ISIM's translation estimation error, both in mean on the left and covariance on the right, which can be dismissed as machine noise. Same goes for the orientation estimation error. Now, finishing with Ruby, we can cover now iX-BSP, starting with the formulation of the original belief explaining problem. We already saw this formulation when the expectation over all future measurements is the main reason for its intractability. This formulation has a special case resulting from a very common simplifying assumption called maximum likelihood, or ML. Instead of considering all possible future measurements, we consider a single sample, which is the ML sample. So under the ML assumption, we get rid of the expectation and are left with a more tractable form. We still consider the full formulation. When we open up the expectation, we can receive the following, where P of Z, giving propagated history, represents the probability known as the measurement likelihood. Since this is intractable due to the expectation over all future measurements, we approximate the expectation by sampling measurements. Sampling n samples for each future step from the original distribution would result in approximation of the objective value. For comparison, under ML assumption, we receive a simpler formulation. Now that we understand the formulation, why should we want to use expectation in the first place? Why not just use ML approximation and avoid dealing with expectation intractability? So this simple simulation examines the effect ML has over the estimation. We took a Gaussian prior on a robot pose, mean at the black square, and 2 types of landmarks, high and low, with high and low uncertainty. The robot considers 2 candidate actions, either a step left or a step forward. Each colored pixel denotes a possible ground truth within the 1 sigma range and the resulting cost value. Although left is statistically favorable 75% of the times, MLBSP chooses forward. So ML approximation might result in suboptimal performance. Now, let us review relevant research in incremental decision-making under uncertainty. While extensive research efforts have been made in the aforementioned planning problem, only 3 considered some form of planning reuse, yet undersimplifying assumptions. Kourniawati and Yadav created an adaptive belief tree, building on partially observable Monte Carlo planning. Use an offline calculated policy. When given as an input, the segments of the policy affected by posterior information. It freshly samples them. While considering Gaussian belief under maximum likelihood assumption, Chavez and Ostis utilized the fixed shared location for all candidate action for calculation reuse, and Kopitkov and Indelman utilized an augmented matrix determinant lemma to avert from belief propagation under information theoretic cost. Till this day, to the best of our knowledge, incrementally reusing decision-making under uncertainty has not been done for the general case. Next, we review iX-BSP, starting with its main contributions. A novel paradigm for incremental expectation belief system planning with selective resampling of future measurements, identifying the problem of iX-BSP with selective resampling as a multiple important sampling problem, and provide with the proper estimator using the balanced heuristics. Statistical comparison of iX-BSP to calculate expectation from scratch, as well as introducing the wildfire approximation to iX-BSP, enabling to controllably trade accuracy for performance. We also supply bounds and empirical results for the effect wildfire holds over the objective value. We demonstrate how iX-BSP could also benefit approximations of X-BSP, for example, IML. Comparing IML to ML in both simulation and live experiments. Now, for us to understand the governing principle of iX-BSP, let's compare 2 planning sessions of time k, the one below, and time k plus L, the one on top. First, we can see that up to time k, they share the same history. In the next time interval between k and k plus L, we have the first possible difference resulting from predicted measurements below and actual measurements on top. Although the next interval relates to future time for both cases, this future is conditioned by a different history, hence also possibly different. And the last time interval represents the extent of the horizon overlap between the 2 planning sessions. Building on this comparison, let's review the governing principle of iX-BSP. We would like to use the plan from time k to incrementally create the one of time k plus L. So the first segment with the shared history should not be changed because they're the same. We incrementally update the second segment with the posterior information using, for example, Ruby methodologies. At this point, we have identical beliefs up to current time. For the next time interval, we selectively resample future measurements to facilitate a representative set of the measurement likelihood probability. For measurements that we reuse, we can take the appropriate already calculated beliefs and update them with the posterior information like we did in the first segment. For the last time interval, since we do not have any information to reuse, we calculate the plan from scratch. Now, let's see an illustrated example of X-BSP followed by iX-BSP, which will reuse the first planning session. In order to adhere to the KISS principle, we assume a single candidate action, 2 samples per belief, and a planning horizon of 3 steps ahead. Assuming we completed inference for current time t equals 1, the belief x1 given 1 denotes the belief at current time. Belief uncertainty is illustrated by the ellipse. And next, we need to execute the belief system planning to decide on the next action. We do here X-BSP, consider U1, U2, U3 sequence. We propagate the belief with candidate action U1 to obtain the propagated belief and sample measurements. Since we do not have access to the measurement likelihood, we sample states and given those states measurements based on the following equality. Now, we're sampling 2 states, and for each, a single set of measurements. Consider each of the sets and the propagated belief to obtain the posterior belief for future time 2. And again, for the second horizon step, propagate future beliefs, sample measurements, sorry. Okay, so we propagate the future beliefs, sample measurements, and calculate the future beliefs. And for the last horizon step, again, we propagate the beliefs, sample measurements, and calculate future beliefs. Now, for visual reference, this is what ML-BSP would look like. At each horizon step, we have only one candidate belief created using a single measurement sample, more specifically, the most likely one. Now, for each belief, we calculate the reward and the cost value. The reward or cost value. The reward of the same action are averaged together, and the objective for each action sequence is calculated. The action sequence with the best objective value is chosen. We then perform this action, get new measurements, and perform inference for time t equals 2. Next, we execute iX-BSP to decide on the next action we should take. First, we check which of the available beliefs for time 2 is closest to the one we have. The more different it is, the more we need to update. So we aspire for the closest one available. After some consideration, we chose to use the square root Jeffreys divergence, although any other belief distance function would do. We define some critical value epsilon c as the threshold for considering a belief as worth reusing. Once we chose a belief, we consider all of its children as candidates, as well as discarding the rest. We consider the U2, U3, U4 sequence and propagate the belief with the next candidate action. We obtain the propagated belief. We consider all samples, reuse representative samples in blue, and resample the rest. Here we can see a simple example for the meaning of representative sample. On the left, a set of green samples based on a planning time k. On the right, over the aforementioned, 2 propagated beliefs based on planning time k plus 1. We can see that the samples better represent the blue distribution than they do the red. So for reuse samples, we reuse the beliefs. We update these beliefs with info from time 2. For the rest of the samples, we need to calculate the beliefs from scratch. We propagate the future beliefs, consider all samples, reuse representative samples, for reuse samples, we reuse the beliefs, update them with the information from time 2, and resample the rest of the measurements, and calculate the appropriate beliefs. We propagate future beliefs, and the last horizon step, and we use iX-BSP because we have no other information. Well, we sample measurement, calculate the beliefs, and for each belief we calculate or update the reward cost value. Now, we need to weigh the rewards of the same action together. Based on color coding per action, samples were taken from multiple measurements PDFs, meaning we're required to use importance sampling for proper weighting. For this toy example, we have a max of 2 different PDFs per step in white and blue, meaning the weight corresponding to this belief, for example, is given by this ratio. For the general case, each measurement can be sampled from a different measurement PDF. So the objective for each action sequence is calculated, and the action sequence with the best objective value is chosen. As each planning horizon can involve measurements sampled from multiple different distributions, we identify the problem as multiple important sampling problem, and the objective estimator is thus given by this equation, where for the weights, we use the balance heuristic, resulting with the nominal distribution divided by weighted sum of all distributions used at each step. Now let's put iX-BSP to the test. We compare planning time of iX-BSP and standard belief system planning using expectation. We use 10 randomly generated maps, each with 2 goals. The robot is required to visit both goals with an objective that minimizes distance to goal and maximizes the information gain. On each map, we ran 20 rollouts, meaning entire mission run, each with a different sampled initial ground truth position. The robot is equipped with a stereo camera and has no prior knowledge over the environment whatsoever. We considered known models with Gaussian additive noise. We compare planning computation time, excluding the last horizon step, which is identical between the two. So these are the 10 maps used for this analysis, each with 2 goals and randomly generated landmarks. From left to right, we can see the cumulative planning time, excluding the last horizon step, the estimation error at reaching the goal, and the norma of the appropriate covariance. We can see a considerable reduction in computation time without affecting the performance. We now introduce an assumption to iX-BSP we call wildfire. This assumption is not an integral part of iX-BSP. So iX-BSP does not introduce approximations to the iX-BSP solution, as it updates all posterior information, but sometimes a belief might be already close enough. We introduce an approximation we call wildfire. The wildfire threshold, epsilon wildfire, sets an upper bound to consider beliefs as close enough, meaning we now have 3 categories to beliefs under the use of wildfire: close enough to reuse without any update in the green area, close enough for reuse in the yellow area, or too far off for reuse, meaning over the epsilon C barrier. Once a belief meets the wildfiring condition, all its dependents are considered as wildfire as well, and hence the name. So for epsilon wildfire equals 0, we consider only identical beliefs as close enough. And for epsilon wildfire equals infinity, we consider all beliefs as close enough and never update anything. From these 2 edge cases, we can deduce that the choice of epsilon wildfire would have a direct impact over the objective value. Under an assumption of alpha holder reward function, we derived bounds for this impact. The bounds over the objective error is a function of the holder parameters, the wildfire threshold, and the belief distance propagation along the planning horizon, which is a random variable. The incremental distance is defined by the difference between the square distances of 2 consecutive planning times. So it's time to put wildfire to the test as well. We compare planning time of iX-BSP with and without the use of wildfire. We use exactly the same scenario over the same 10 maps. On each map, we ran 20 rollouts, entire mission run, each with a different sampled initial ground truth position. We can easily notice the considerable saving in computation time under wildfire, and thanks to the choice of a relatively small threshold, we can see no impact over the estimation accuracy. It's important to remember that the wildfire is still an approximation and does in fact affect the objective value, as so potentially the obtained accuracy. Next, we empirically examine this effect. So we would like to provide empirical results to the objective error. We need to perform planning from 2 beliefs sharing a history with a specific distance between them that will be the epsilon wildfire distance. We propagate a belief with predicted on the right and actual on the left measurements. To control the distance between them, we introduce specific noise to the actual action. And this is what we get. for objective of maximizing information gain and minimizing distance to goal. We can see that the objective difference between two planning sessions grows with our choice of wildfire threshold. So the larger the allowable distance between beliefs, the larger the deviation in objective value. We will now use the common ML assumption to create IML-BSP and show how the iX-BSP paradigm can be used on approximation of X-BSP. So as iX-BSP was formulated over the original auto-approximated problem of X-BSP, we believe it can also benefit all existing approximations of X-BSP. To support this claim, we introduced the ML approximation to the iX-BSP and denote the result as IML-BSP. We can see here the formulation without the expectation. And this corresponds to only approximating the expectation with a single sample sequence of measurements rather than all possible ones. Now, let's put IML to the test. We compare planning time of IML and standard malicious planning using ML. We use a randomly generated map with two goals. The robot is required to visit both with an objective that minimizes distance to goal and maximize information gain. We ran 1,000 rollouts, each with a different sampled initial ground truth position. The robot is equipped with a stereo camera and has no prior knowledge over the environment whatsoever. We considered known models with Gaussian additive noise. We can see a considerable time reduction in planning computation time with mild to no impact over the estimation results. Finally, we test IML on a real robot. Now, throughout the experiments, both methods chose the same actions as optimal. So we will not compare the estimation accuracy. What we compare here is the planning time of IML and ML-BSP. We use the Pioneer 380 robot equipped with a Z stereo camera and the Hookio LiDAR. The robot is required to visit a set of goals with an objective that minimizes distance to goal and maximizes information gain. We ran two experiments, 35 meters and 148 meters long. The robot has no prior knowledge over the environment whatsoever and no usage of offline calculations. We considered known models with Gaussian additive noise. Now, this is the estimated path of the 35-meter long experiment. The goals are numbered in purple. Robot estimated poses are in blue, and landmarks are in black and red. We can see 4 pictures from the Z camera with extracted landmarks marked in green. On the left, we can see a cumulative planning time of the entire mission for both methods, broken down to the contribution of the first 3 horizon steps in gray and the identical last horizon step in black, the one we discarded till now. While the latter remains unchanged as expected, we have a considerable reduction in the former. On the left, we can see, on the right, we can see the per step performance, where the timing of the first planning session after each goal is identical because we have nothing to reuse. Here on the left, we see a familiar graph of added factors per planning session. The blue line is the number of factors added in the last inference session. The red line is the part of them involving existing variables, and the yellow is the part of them predicted with correct data association and reused, and then the reused planning session. Once again, the red line represents the best we can do without predicting new variables. And the right graph shed more light on how we can do better, as the black line is the number of factors deleted from the reused plan in order to match the current one, which again mean that we can improve the computation time by using more sophisticated prediction mechanisms. Similarly, this is the estimated path of the longer 148-meter experiment. And the timing results. Again, we can see the considerable reduction in computation time without affecting the selected actions. And again, we can see that with better prediction mechanisms, we can do better. So to briefly conclude, we introduced a novel concept of joint inference and planning we call JIP. Inspired by JIP, we created two new approaches for inference update, Ruby and belief system planning, iX-BSP. Ruby provides efficient inference update using precursory planning session calculations, while iX-BSP provides efficient belief system planning by incrementally updating previous planning calculations. JIP, consisting of Ruby and iX-BSP, provides with an exact solution to the original standard plan act infer system with a reduced computational effort. This new approach of symbiosis between inference and planning might also pave the way into abilities we have yet to discover. So before taking any questions you might have, I would like to thank my family and friends on the one side and Vadim on the other for supplying the necessary opposite pooling forces, which helped me complete this research while keeping my questionable sanity intact. Thank you all for listening, and I'll be happy to answer any questions if you have any.
All right, thanks, Elad. Any questions?
Yes, please.
Yes, go ahead.
Hi, Elad. Beautiful presentation. Thank you. Regarding the wildfire part, you've mentioned the alpha holder cost or reward functions. What alpha holder functions did you use, and how did you analyze the parameters? I mean, you have the coefficient, etc.
Okay, so basically, I haven't used specifically alpha holder function. The analytical derivation we provided for the bounds use the assumption of alpha holder functions in order for us to be able to actually derivate the bounds. Personally, I think that this bound is true, not specifically this one, but the connection between the choice of epsilon wildfire and the impact it has on the objective values is true regardless of the type of objective function you have. So what we actually did regarding the bounds, which there they are, is basically just analytical work.
Okay, thank you.
All right. More
Not all
questions?
at once.
Okay. Any more questions, maybe? No questions. All right. In this case, let us thank Elad again. Thank you, Elad. And I guess we'll stop here.